Okay, my name is Myron Sherman. I am from Drake University, and I'm going to talk about evaluating IGS tasks. IGS meaning interactive geometry software, also known sometimes as dynamic geometry software. So the question that we seek to answer in this brief talk is how do we as teachers evaluate and select tasks that will use technology to support students' high-level mathematical thinking? So we're looking at evaluation of tasks. What's a good task in terms of how it uses technology? One we'd say is that it supports students' high-level mathematical thinking. So that's what we're going to talk about. Um, so I developed this framework with a colleague at East Carolina University, Charity Caton, and we published this called Use Appropriate Tools Strategically for Instruction in the Mathematics Teacher. So you have that reference there if you want to look at that for more detail. But just by way of introduction, this is the framework. But there's way too much here to try to talk through it this way. I just wanted to kind of give you the big picture. We have these goals in terms of the rows, and then in the columns we have this amplifier and reorganizer. So I want to begin with talking about where do we get these goals from. We got them from Sinclair's design principles. She had 5 design principles that she published, and we had 3 of them that were relevant for what we were looking at. So as opposed to reading all of these, I want to pull out the important part of each of these 3. So this first one says if we're asking students to drag, observe, or deduce. The second one, when a question invites exploration. And the third one, a question can surprise, and that could lead to and support experimentation. So we pulled those 3 out and said, well, if we're asking students to drag, observe, or deduce, then the goal could be to make mathematically meaningful observations. And then the role of interactive geometry software in that case would be to provide the affordances that would support students in making those observations. A second goal could be mathematical exploration. So we want students to explore some mathematical concept or idea, and in that case, the IGS has to provide some alternative paths so that they can explore in different ways. There's a certain open-endedness that is necessary for mathematical exploration. And then thirdly, we might want students to make, test, and revise conjectures so that we see this kind of associated with experimentation. So again, the role of IGS in this case is to provide feedback that would support that, where students could test their conjectures and then possibly revise them based on the feedback that they're getting from IGS. So we want to take each of these now and kind of go through each goal. Well, first talk about amplifier and reorganizer. So what do you mean by that? Amplifier, basically it means that we're using technology in a way that makes things more efficient, but could be done without it. Whereas reorganizer really allows us to do things or get at things that we couldn't get at without it. And obviously here, in this context, we're talking about instruction. We want to be able to engage students with ideas or behaviors or thinking that would be difficult to do without the use of technology. So this is basically the first row of that, massive looking piece of text that I put at the beginning. So again, the goal here, make mathematically meaningful observations. The question that you might ask as a teacher is, did the sketch and prompts use the dynamic affordances of IGS in a way that would be difficult or impossible to replicate without it? And the key here is the dynamic. All right, so as an amplifier, students might be led to create a number of static examples and then perhaps maybe record them in a table. So this is kind of a drag and stop action. You drag, you stop, you record an observation or a measurement, and then you do it again, and then you do it again, and then you have this set of examples basically that you've created, and you just reason from the numbers. So at that point, it's kind of like we have these examples and we kind of discard the sketch. We're no longer looking at the sketch anymore. We're just looking at patterns and numbers. Whereas as a reorganizer, the sketch would allow for continuous dragging, and students would be led to examine the measurements or the relationships in the sketch dynamically as you're dragging continuously as opposed to a drag and stop motion. So here the focus remains on the sketch. Students are able to kind of see things in real time that would be difficult or nearly impossible, really, if you think about creating the same thing over and over again. So we'd like to give one example of each of these. So here's an example of an amplifier, in the sense that this is just creating specific examples and asking students what they notice. It's just creating a set of examples. So the dynamic aspect isn't really being brought into play here. And again, when we talk about creating a set of examples, that's not something we necessarily need technology to do. And I contrast that with this task. We'll look at the prompts first, and I want to emphasize when we're looking at these, we're looking at the sketch and the prompts together, the prompts being the questions that students are meant to engage with. We want to look at those together because the prompts really guide students in terms of how they're intended to use the sketch. So here we're going to see a dynamic representation of a box and whisker plot and a bunch of data points that students can drag, and then they're going to answer these questions in terms of, so a shorter question, Q8. How can you move a single data point without changing the mean? All right, so students can then interact. And this is what the dynamic sketch looks like. You can grab these data points and you see this connection among this dynamic connection among the representations. You can drag the individual data points. You can see how the box and whisker plot changes, how the mean changes. You can see the mean and median as well as Q1, Q3 and the individual data points. So here students can drag continuously to see how these different representations react and are connected in real time.